Todo-san received his PhD from University of Tokyo at 1996. And after that, he moved to the ISSP, University of Tokyo, as a research associate. If my memory is correct, Professor Takayama Sensei group. And after about 2 years postdoc at ETH Zurich, Matthias Troyer's group, he came back to Japan as a lecturer at the Department of Applied Physics, University of Tokyo. And after that, he moved to the K-computer at Kobe about 4 years. And after that, he came back to Tokyo again as an associate professor at the Department of Physics. And now he is a full professor of the Department of Physics, University of Tokyo. And Todo-san is a world-leading researcher of large-scale computational physics. And also, he made a great contribution to the community of the large-scale numerical computation and its applications. So actually, he is now group project leader of Sustainable AI project, which is one of the biggest projects conducted by the Japanese government. And I guess he's very busy, but he kindly gave a talk today about Markov-Chain Monte Carlo in Tensor-Network representation, which may be relevant to our extreme universe collaboration. So please enjoy his talk. Todo-san, please.
Thank you very much for kind introduction, and thank you very much for giving me opportunity for this colloquium. Okay, so today I'd like to talk about some combination of the Markov-Chain Monte Carlo and the Tensor-Network technique. Okay, so the outline of my talk is like this. So first, I would like to introduce briefly the Markov-Chain Monte Carlo and the Tensor-Network representation. And then we introduce some sampling technique to the Tensor-Network construction. And then I will give the detail of a new method, Markov-Chain Monte Carlo in Tensor-Network representation, and give some result. Okay, so first, let's start with the introduction of the Markov-Chain Monte Carlo. Okay, actually, the stochastic approach in computational physics is important, but it is very difficult to understand by our brains, since our brains are not just are just not wired to do probability programs very well. Actually, since the invention of Markov-Chain Monte Carlo, there are lots of development or improvement about the Markov-Chain Monte Carlo. For example, the idea of perfect sampling. By using this perfect sampling, we can sample perfectly independent samples from Markov's chain. It is very amazing, but it is good mathematically. But I don't know if it is practical or not. But okay, so another example is the extended ensemble method, exchange Monte Carlo, or one random sampling, or multi-canonical method. And the interesting thing is these algorithms realize equilibrium distribution immediately after quench. For example, changing energy or changing temperature and so on. And also it can help us to sample extremely rare events. Okay. And another improvement is the exact order n sampling for long-range interactive systems. or Markov-Chain Monte Carlo without detail balance. Recently, this MCMC without detail balance has been developed and investigated very well by many groups. Okay, so actually, the advances in Markov-Chain Monte Carlo have happened in many different levels. Okay, so first we have to consider about the representation of the model that can be so that it can be simulated by the Markov-Chain Monte Carlo. The representation means first we have to define the configurations and its weights. Okay, so in the case of Ising model, configuration is trivial. The array of spins up down, and the weight is the Boltzmann weight. But for example, if we want to simulate quantum, for example, quantum spin systems, first we introduce path integral representation to map the original d-dimensional system into the d plus one dimensional classical system. And the path of the spins is the configurations we want to sample. And the weight is defined for the path integrals. Okay, then we can choose an ensemble. So we can introduce some extended ensemble method. It is a combination of ensembles, different temperatures, and so on. And okay, so in this figure, each circle denotes each configuration. For example, this means the all spin up state, and this is the all spin up except one spin down, and so on. And we define the weight for each circle. Okay, this is the representation, and we consider the generation of a set of candidate configurations. Okay, from each configuration, we propose some update. Okay, one spin flip or cluster flip and so on. So this edges denotes the possible proposal from each configuration. Okay, and then we can choose the transition kernel or probabilities for each transition. So the standard method is the Metropolis or heat map method, but recently we introduced some irreversible kernel or event chain technique to speed up the recreation of this network. And also we can improve the algorithm for generating configurations according to transition probabilities, for example, n-fold way or the n algorithm and so on. So this way, we have many advances or improvement in Markov-Chain Monte Carlo, but there is a severe problem, negative side problem, of course. So in the path integral representation for frustrated magnets or fermion systems or real-time dynamics, the sample weight becomes negative or even complex. Okay, so this means the weight cannot be understood as a probability. So we consider the absolute value of the weight for calculating, assign the probability for each configurations. And we use a reweighting technique to recover the original ensemble. But the problem is that average sign becomes exponentially small by the cancellation at lower temperatures or longer time and the larger system size. Okay, this is an example of the anti-ferromantic Heisenberg model on Kagome lattice. So on the Kagome lattice, we have many triangles. So we have frustration. And this is the temperature dependence of the average sign blue dots. As you see, the average sign becomes exponentially small at lower temperatures. And accordingly, the statistical error of specific heat, statistical error diverges exponentially. Okay, that's the problem of the negative sign and negative sign. And the negative sign also appears in the simulation of quantum circuits. Okay, this is a simple 3-bit qubit system, and we have many single qubit operation, Adamar gates, or 2-qubit operation, control Z or control X or something like that. And okay, in this simple quantum circuit, we start from 000 state, and every time we encounter the Adamar gate, the state bifurcates into 2. Okay, so since we have 3 Adamar gates here in this circuit, so we have 8 different states at the final state, but some of them cancel with each other due to the sign. Okay, so finally we only have 2 states, 000 or 111, with the same probability. Okay, so if we want to simulate this quantum circuit by using sampling, so we choose one of state 000 or 100 at this Adamar gates, so on. So we have 8 different states, different paths. But at the final Adamar gate or this C control Z gate, we have extra minus sign. So actually, this 001 state and 100 state has 0 weight by the cancellation. And actually, if as the quantum circuit becomes deeper and deeper, more states vanishes by interference. So it's a negative or complex sign problem in the simulation of quantum circuit. Okay, so the statistical error of the Markov-Chain Monte Carlo can be described like this. Okay, so this sigma naught square is the population variance. So it is it is calculated from the distribution of quantities, for example, magnetization square of energy or something like that. And this sigma naught square is determined by ensemble. So if we choose ensemble, this is determined and we cannot change. And M is the total number of Monte Carlo steps. And if we can sample the configurations statistically independently, the final statistical error is proportional to the sigma naught square divided by M. But in the Markov-Chain Monte Carlo, we produce the next configuration from the previous one by using a stochastic process. There is a correlation. So the correlation between the successive configuration is characterized by this tau int. This is the autocorrelation time or integrated autocorrelation time. And if this tau int becomes large, the effective number of independent samples decreases like this, m divided by 1 plus 2 tau int. Okay, so we only have every 2 tau int steps, we have statistical independent samples. Okay, and this tau int is determined by the Monte Carlo dynamics. So we can reduce this tau int, for example, by introducing cluster update or some non-local updates or other techniques. Okay, so for reducing this tau int, many algorithms like this have been proposed. Okay, for the system with negative sign problem, the situation becomes worse. So we have extra factor here, S square. Here, S is the average sign. And actually this S becomes exponentially small for low temperature or longer time or larger system. So the final statistical error becomes diverges exponentially. Okay. So this is the introduction of Markov-Chain Monte Carlo and the problems in the Markov-Chain Monte Carlo. We have two problems, autocorrelation problem and the negative sum problem. Okay, so let me briefly introduce the tensor network. Okay, so we consider some, okay, let's consider some n qubit or n spin system. Wave function is given by the linear combination of the basis state, up or down or something like that. And this coefficient, we have many coefficients. For the n spin system, we have e to the power of n coefficient, different coefficient. Okay, so if you want to represent this wave function on the computer, the memory cost is e to the power of n. And this C can be regarded as n leg or rank n tensor like this. Okay, so I think most of you are very familiar with this tensor representation, but I just briefly mention about. Okay, we use some graphical representation of tensors, and actually zero leg tensor. This is nothing but a scalar. It's denoted by just a circle, and one vector is one leg tensor or rank one tensor, and we represent it as a circle with one outgoing edge, and two leg tensor is a matrix, and n leg tensor is like this. And in general, the computational cost and the memory cost about the tensor operation is proportional to the exponential of n. So that's the problem in the tensor network method. And actually, this tensor representation we can find anywhere, everywhere. This tensor network representation. For example, we can represent the probability distribution function, n-dimensional probability distribution function, by using tensor, for example. And actually, we can represent a grid data, something like images or some field by using tensors. Okay, so for example, this two-dimensional data, field data, xy, we represent this x coordinate or y coordinate by using a binary number. So x1 to xn and y1 to yn represent 0 or 1. Okay, so this way we can represent, for example, the 256 times 256 image by 16 leg tensor. And also, for example, in the neural network, we have a weight matrix. Okay, so this is the neuron, and these are the neurons. And this weight matrix W is actually a matrix. And also, by this technique, we can represent this weight matrix as tensors. Okay, so since the cost for this large many-leg tensor is exponential, we want to decompose of this many-leg tensor into product of small tensors. Okay, so this line edge is connecting tensor means the taking a summation between the tensor, summation of about the common indices. Okay, this is called contraction. And after the tensor decomposition, we have a tensor network instead of a large tensor, many-leg tensor. Okay, so the advantage of tensor network representation is first, we can reduce the data size from the exponential n to order n. And we have a freedom in taking the contraction of this tensor network. And actually, we can introduce highly accurate approximation based on SVD for this tensor decomposition or tensor contraction. Okay, so actually, in many cases, we have an exact representation of tensor network. For example, the classical partition function of the classical system, for example, the Ising model, can be represented by the tensor network exactly. So by taking the contraction of the tensor network, we can calculate the partition function of the Ising model or statistical model. Okay. But in many cases, such a exact representation is not available. Okay, here I just mentioned about the relation between the quantum circuits and the tensor network. And actually it is trivial to map the quantum circuit into a tensor network. The one qubit operator is represented by a two-leg tensor matrix, and a two-qubit operation can be represented by a four-leg tensor or 4x4 matrix like this. Okay, and by the initial state, it's a tensor product of two-dimensional vectors. So each zero state can be represented by vector like this. Okay. And then by taking a contraction, we obtain the final quantum state or wave function like this. This is the three-leg tensor. Okay, so if we take a contraction from the initial state to the right, like this, it is equivalent to a Schrödinger or state vector simulation. But for example, if we want to evaluate some amplitude in the final state, for example, the 111 state, so we want to evaluate the inner product in the final state and this 111 state, the tensor network can be written like this. And if we contract this tensor network, we will obtain some scalar, just one complex number. And the advantage of tensor network representation is first, the order of contraction does not change the final result. So we can take a contraction from left to right, or right to left, or bottom to top, or vice versa, as you like. And this freedom, or the freedom in contraction order, sometimes makes us possible to reduce the computational cost. But actually, the optimization of contraction order is very, very difficult problem. It is as the Sharpe-Hart problem. But many heuristics have been proposed. And also, we can introduce some technique called slicing. So we can fix some tensor indices, and that reduce the cost for contracting the tensors for each slice. And we can take a summation of fixed value patterns by using a parallel computer, for example. Okay, so for example, this paper is a kind of state-of-the-art tensor network simulation. So they use many heuristics and many techniques and succeeded to contract huge tensors by using supercomputer, and they won the Golden Bell Prize in 2021. This Golden Bell Prize is a kind of Nobel Prize in the computational science. Okay. Okay, so, but in many cases, we have to use approximation. Yes. So actually, there are two approaches in the Tensor-Network method in statistical physics or quantum mechanics. Okay, first one is the renormalization approach or Lagrange approach. So in this approach, we have a tensor network that represent partition function or some final result. Exactly. Our task is construct such as a very complex tensor network to obtain the final result. Okay. So for example, the two-dimensional Ising model, partition function can be written as this two-dimensional square lattice tensor network exactly. But the taking a contraction is exponentially hard. So we introduce some coarse grain or approximation to evaluate the value of tensor network. Okay, this is renormalization approach. Another approach is the variational or Hamiltonian approach. In this approach, the tensor network is used as some approximation or variational wave function. Okay, so by optimizing the elements in the tensor network, we have a good approximation for the wave function or other target function. Yes, this is called variation approach. But in both cases, we have to construct the large tensor network. But exact construction cannot be done in higher dimensions. We introduce some approximation, and the accuracy of approximation is controlled by some quantity called bond dimension, D or chi. Okay, I will explain the approximation. The most basic one. Okay, tensor network, tensor renormalization group. Okay, in this approach, first, we have many four-leg tensor here. First, we decompose each tensor into two. Okay, for example, this tensor is decomposed into 2 or 2, something like this. And after the decomposition, we have a network like this. And then we contract these four tensors, okay, into one tensor like this. And after the contraction, we have this network. The number of tensor becomes smaller. Okay. So the number of tensor is square root 2 divided by 2 after this renormalization. And of course, if we decompose this tensor exactly, the dimension here between these tensors becomes exponentially large as you renormalize many times. So we introduce some approximation, SVD, to keep the bond dimension below some threshold. This is called D. Okay. So the computational cost for this tensor renormalization group is D to the power of 5, and the memory cost is D to the power of 3. Okay, D cubed. This is the most standard or basic renormalization group approach. And actually, after the tensor renormalization group, many improvements have been developed or proposed so far. Okay, so I think there are 3 or 4 different approaches or different directions about the development of the method. And the first is for improving accuracy with fixed point dimension. So, for example, we can include some environment effect to obtain a better approximation, or we can remove local correlations that this local correlation reduce the effective point dimension, but in this approach, the computational cost increases significantly. Okay, so we recently proposed some approach called PTRG, bond-weighted TRG. By this method, we can improve accuracy without increasing complexity. Okay, another direction is just reduce the complexity or computational cost. Sometimes the accuracy becomes worse, but the complexity is reduced at the same time that we have higher accuracy with the same fixed computational cost. Okay, I will explain this later. And another approach, another direction is the generalization to higher dimensions for fermionic systems. Okay, so I explain. Okay, HOTRG. This is the okay. So this higher order normalization group, we introduce some isometry or projector between the tensors here, and reduce make a coarse grain of tensor, something like this. And the advantage of this method is that we can apply this method in higher dimensions. Yes, 3 dimensions, 4 dimensions, and so on. And it is more accurate than the standard TRG in 2 dimensions. But the computational cost becomes higher. And actually the computational cost in D dimensions is D to the 4 times small d minus 1. So it is huge. That's the problem in higher order tensor renormalization group. So we introduce, recently we have developed an isotropic tensor renormalization group method. This method can also be applied to higher dimensional system, and the cost is much smaller than the HOTRG. Another direction is the method, more accurate method with the same computational cost. Okay, so yes, and the key point of this, or central idea of this ATRG, is avoiding the tensors with many legs. Okay, so in the HOTRG, this cost comes from the contraction of these tensors. So we have 4-leg tensors and 3-leg tensors and so on. But in ATRG, we only use 3-leg tensors for 2 dimensions. Okay, this way we can reduce the computational cost. And same idea. Okay, so I skip this. Okay, the same idea has been used in this method, CATN. Okay, so okay, in this method, they decompose the initial tensor into MPS like this. So in this tensor network, all the tensors has 3 legs at most. Okay, and the renormalization have been done, only using three-leg tensors like this. Okay. Okay, so let me summarize the advantage and disadvantage of two approaches, MCMC and Tensor-Network method. Okay, in the MCMC, there is no systematic error. It gives a consistent result in long time limit. Okay, as long as the balance condition and the ergodicity are satisfied. And usually the computational cost increases only linearly. And it is trivial to parallelize the MCMC simulation. These are the advantages of Markov-Chain Monte Carlo. But the disadvantage is the slow convergence of statistical error. M is the number of Monte Carlo steps, and the negative sign problem. On the other hand, in the Tensor-Network method, by increasing the bond dimension D or cutoff D, the accuracy is improved very rapidly. This is the most biggest advantage of Tensor-Network. And also, since it does not use the stochastic process, we have no negative sign problem. But the disadvantage of Tensor-Network method is the systematic error or bias due to the final bond dimension D and the rapid growth of the computational cost. And it is not very trivial to extend the method for higher dimensions. These are the disadvantages of Tensor-Network method. Okay, so these two methods has their own advantages or disadvantages. So we want to remove this disadvantage by combining methods. That's my motivation. Okay, so we want to combine the Tensor-Network with Markov-Chain Monte Carlo and remove the problems in both methods. Okay, so actually what I want to propose is the new definition of configurations and weights for the Markov-Chain Monte Carlo framework. Okay, we use a Tensor-Network as a representation of representation for the Markov-Chain Monte Carlo. And as I show below later, this new representation works very well. And actually, as I said before, the population variance, sigma naught square, is determined by the representation and cannot be changed by the update scheme. But here I introduce a new representation. We can reduce the sigma naught square by the new method, and that can help us to reduce the negative sign problem as well. Okay. So before introducing our method, I introduce some so-called projector formulation of Tensor-Network method. As I explained before, the HOTRG, higher order tensor renormalization group method. So we introduce projectors or pair of isometries between the tensors, okay, for X direction and Y direction alternatingly. And after constructing these tensors, we have constrained tensor network like this. Okay, and actually, I think any tensor network method can be formulated as a project by using a projector. Okay. In the original tensor renormalization group, they use singular value decomposition of a tensor like this. in this tensor network decomposition, we use SVD. Okay, this is the matrix representation of the original tensor, and we use SVD and truncated smaller singular values, and we will have these two tensors like this. But this procedure can be rewritten by using the projector defined like this. Okay, this WL and WR star defines the projector, and by inserting this pair between A and B, we have the same result. Okay, so I think any tensor network method using SVD can be reformulated as the projector-based tensor network normalization. Okay, so this way, the original TRG can be reformulated like this. Okay, so we insert the projectors between the tensors and projectors between tensors and so on. So that in this TRG, what we are doing is we choose these projectors inserted between the tensors and contract these large tensors. Okay. And we have two n initial tensors and n-4 projectors like this. Yes. Okay, this is the projector formulation. Okay, we use this projector formulation in order to introduce the MCMC. Okay, okay. So another example is ATRG and CATN. They can be also reformulated by using a projector method. Okay, actually, in this procedure, we have to swap the leg from this configuration to this between tensors. But this swapping legs, okay, this one can be written as the inserting projector like this. Okay, so I think any tensor network renormalization method can be reformed in this project. Okay, so actually the basic idea was proposed 7 years ago by Andrew Ferris in this paper. So they propose some sampling method of the projectors. Okay, I think this paper is very important and very interesting, but it was not published. And the problem here is in his method, the variance of the final result cannot be controlled. That's the biggest problem for the practical simulation. Okay, let me explain his idea. Okay, so this is the example of the so-called boundary MPS. Okay, so we have square lattice of tensors like this, and for the we want to coarse-grain these two rows into one by inserting projector here. Okay, by repeating this procedure, finally we have a one-dimensional chain that can be contracted very easily, like a transfer matrix. And his idea is, instead of using the best projector at each point, we sample the projector stochastically. So actually, each projector perform a projection from R dimensions into D dimensions. So we choose D basis vectors in R dimensions. So the combination is this, very large for large R. But yes, and among these large number of candidates, we choose the new a projector at each position stochastically. And the probability of choosing the projector is chosen so that after summing the this theta denotes the projector index. Okay, by summing all projectors, it gives the identity. Okay, after taking the exact summation about the projectors, this gives the exact result as the original tensor network. And actually, he applied the two-dimensional Ising model. And okay, so the red one is the original TRG. So it has a systematic bias, although it is not very large. But by using this sampling technique, he showed that this systematic bias is reduced, removed completely. Okay, sorry, this is 6 vertex model. Okay, but okay, so this is a summary of this this archive paper, and he proposed a kind of perfect sampling of tensor network construction, and can be applied to other tensor network methods. Okay, but of course, we have to choose the projectors at each position independently. So this method only works for finite systems, but I think it is not a big problem. And it is actually unbiased as long as you calculate the partition function. But if you want to evaluate the free energy or expectation value of physical quantities, it has bias. It is biased since taking a log or taking a ratio between two random numbers is not a linear operation. So it introduces some bias. Okay, but it is not a very serious problem. The most serious problem is it suffers from exponentially large variance. Okay. Actually, at each position, we choose a random matrix, right? And this is nothing but the product of many random numbers. Okay, independent random numbers. And actually, okay, I will skip here. Okay, this is a simple example. Okay, we start from 1, and we multiply many random numbers, C. This is a uniform random number between 0 and 2. Okay, and we multiply this independent random number n times. And of course, the expectation value should be 1. But if we plot the histogram of this xn after n step, n 4, 8, 16, the distribution of this x becomes very, very wide. Okay, actually, this is a log scale. And the average is here, 0 here. Okay. Okay, but for example, after 64 steps, okay, so the typical sample has very, very small number, okay, 10 to the minus 20 or something like that. And only a few sample which has a large contribution dominate this expectation value. So, okay, so it gives a correct mean value, average value, but the variance, statistical variance, diverges exponentially as n becomes large. Actually, the variance is statistical error is exponential square root of n. So actually, their method is nothing but the multiplication of random matrices. Okay, so their method suffers from the exponentially large value. So we propose a method that can control the statistical variance. Okay. There are two approaches. One is the sequential Monte Carlo. Okay, sequential Monte Carlo has the same problems. Okay, so in the sequential Monte Carlo, we prepare many workers samples and represent the final distribution by the distribution of workers. But since the some worker has a very large weight and the final distribution is dominated by the worker with large weights, so we introduce the idea or method called resampling. Okay, this is very essential to the sequential Monte Carlo. So here, okay, so the worker with large weight is divided into many workers, and some workers with very small weight is removed. Okay, this way we can keep the total number of workers and also the variance of weights between workers. Okay, so this is one approach, and I think it works well. For example, yeah, okay, and it is. I think this approach, sequential Monte Carlo, is very suitable for calculating partition function or free energy. But okay, we introduce another approach, Markov-Chain Monte Carlo. Okay, so we have made several changes from the original proposal by Ferris. Okay, so okay, let me go back to this their proposal. Okay, in this method, he choose a set of projectors. Okay, for example, we choose a set of projectors here by using the result of the previous projector. Okay, so he choose a kind of best set of projectors. Okay, but it changed. Okay, so this means, okay, this theta 1 to theta n is indices represent the projector. But here we choose each projector independently. Okay. We introduce some approximation like this. And we prepare a set of projectors by using the standard or improved Tensor-Network method. Okay, so we perform our Tensor-Network renormalization group once and prepare a possible set of projectors. Okay, and Tensor-Network, by using a Tensor-Network, the partition function of the original, the target system can be written as this. Okay, this is the probability, and this is a kind of partition function for a given projector set. Okay, and actually, in our method, this P is a product of each projectors. Okay, so this is the formulation of the representation of the partition function, and we sample these projectors by using Markov-Chain Monte Carlo. Okay, during the simulation, we propose one position and propose new theta according to this probability. And we use a Metropolis Metropolis probability for accepting or rejecting the proposed new projector. Okay, and to calculate this G, this is a result of contraction of under the given projector set. So since we change the projector at some position, we have to evaluate we evaluate the contraction of the tensor network, but since we update only one tensor or one or two tensor, so the update of recalculating this G is typically log n instead of n. This n is the total number of projector or total number of original tensor. Okay, and since we choose the set of projectors before the MCMC, the SVD, singular variable decomposition, are required during the initialization stage only. Okay, so during this MCMC, we just choose a projector and make a contraction. So it includes a matrix multiplication only. So it is very fast. And also physical quantities such as magnetization or energy or other quantities can be evaluated by using the so-called impurity tensor. Okay, so let me show some result. This is the very small system, but for this system, we can calculate these quantities exactly. Okay, so these purple, green, okay, so these four data are calculated with this original TRG plus impurity tensor technique. And actually, the free energy can be calculated very, very accurately by using this TRG technique, but it has a relatively large systematic error for the physical quantities. For example, if you look at the specific heat as a function of temperature, this blue line is the exact result, and D is equal to 1, 2, 3, 4 as a large systematic error from the exact one. Okay, but okay, also in other quantities as well. But by using Markov-Chain Monte Carlo sampling, okay, we use T is equal to 4, very small bond dimension. Our simulation gives exact result, consistent with exact result, although it has a statistical error to some fluctuation, but the result is consistent with the exact result. Okay, and actually, the statistical error from our result, from our method, decreases exponentially as we increase bond dimension D. Okay, so this is the result for the energy and magnetization square at the critical point of the square lattice Ising model. Okay, so these we perform 8,000 Monte Carlo steps, and this purple line or green line is the statistical error by the original metropolis local fleet, and our statistical error is much more smaller than the original one, and furthermore, it decreases exponentially as we increase D. Okay. And actually, if we look at the distribution of physical quantities, energy or magnetization squares, the distribution is different from the original canonical distribution, since our representation is different from the canonical distribution. So this means that we can change this sigma node square, and actually this number becomes smaller and smaller exponentially as we increase bond dimension D. Okay, so by increasing D, we can change the representation gradually, and the distribution of physical quantities becomes narrower, narrower, sharper, and sharper. Okay, exponential. Okay, so this is another demonstration. Okay, we consider the system with negative sign problem. Again, we consider square latticizing model, but here we set this external field to pure imaginary. Okay, we choose H is equal to I times pi divided by 2 beta. Okay, by choosing this fugacity becomes -1. Okay, so this means the Boltzmann weight is given by this. So we have a -1 negative sign here. Okay. Okay. So at zero temperature, we have all up or all down state, and M takes some fixed value. So in that limit, we have no sign problem. Yes. But at higher temperature, so other total magnetization sector comes into the Boltzmann distribution, and we have a very severe negative sign problem. Okay, so we choose a pure imaginary external field at here on the complex plane of fugacity Z, and at higher temperature, the zero of Lie zero accumulate at higher temperature, accumulate to the negative imaginary time negative axis. So the negative sign problem becomes severe and severe. Okay, so actually this is the result of the standard mesocourse method. At lower temperature, the average sign is 1, so we have no problem. But at higher temperatures, the negative sign becomes average sign becomes 0 exponentially. So we have a divergence in the statistical error in this region. This is the semi-log plot of the sign average sign. Okay, so let's apply our method in this case. Okay, so so this case D 2, 3, 4, 6, 8. This is the result used by our method using different value of D. Okay, and the purple one is the result from the local mesocourse update. Okay, so for very, very small D, D is equal to 2. The average sign decreases at higher temperature as well. The performance is almost similar to the original method. But if we increase value of D, the average sign is improved very rapidly. And for example, D is equal to 8 case. We have no sign problem here. Okay. So yes, we show that since the variance of the if we look at the distribution of Boltzmann weight during the MCMC, the distribution becomes narrower and narrower exponentially in our method. Okay, that's why we can reduce the negative sign as well. Okay, so this is very simple example, but I think this method can be applied in many systems with and without negative sign. And statistical error can be improved exponentially as we increase the bond dimension D in the tensor-network approximation. Okay, so let me summarize the talk. I introduce a combination of Markov-Chain Monte Carlo with tensor-network, and we can reduce the statistical error using the approximation tensor network construction. At the same time, we can remove the systematic bias by sampling singular vectors using MCMC. And actually, the statistical error becomes exponentially small as we increase the approximation by increasing the bond dimension D. And actually, we can improve or remove the negative sign problem in some cases. And the computational complexity of this method is given by this. This D to the alpha comes to the cost of the contraction of the tensor network, and N is from the system size, and log N is come from the update of the result of contraction for each local update. But we only use a matrix multiplication during the MCMC. So I think this method works very well for modern GPU or HPC. And yeah, the similar formulation is possible for sequential Monte Carlo with sampling. And I think this another method has advantage in calculating free energy or partition function. And as I explained before, almost all the tensor network renormalization group can be formulated as a projector method. So we can apply this method in a straightforward way. Okay, that's all. Thank you for your attention.
Thank you very much. Very interesting talk. So now this talk is open for question and comment. So if you have a question, please directly unmute your microphone and ask your question. Is there any question or comment? So may I ask a very naive question?
Sure.
So I'm very curious about the sign problem in this tensor network representation. So in my naive understanding, the sign problem in usual quantum Monte Carlo, probably the sign problem never solved by some local basis changes, I think. So, but in the tensor network representation, probably the isometry inserted between the many tensors correspond to some base change in the sense of tensor network, usual tensor network. So why the sign problems this appears in this your simulation just by increasing bond dimension D. Basically, the representation of the basis is not significantly affected by increasing just the bond dimension D, but why so drastic change occur in in the case of
Okay, so I have no definite answer, but for example, if you consider the quantum Monte Carlo in usual SG basis. Okay, it has a sign problem. But if you take integration, the path configuration during the tau is equal to 0 to beta, so still you have a configuration SG at tau is equal to 0. But in that case, there is no sign problem. So by taking a summation of many exponentially large configurations, you can remove the sign problem. This is one example, and actually, in our method, we taking so that in the original spin basis, we have negative sign problem, but Okay, I think it is not very easy to present this one, but for a fixed projector configuration, it contains many uh, classical spin configurations. It is a linear combination of uh, original spin configuration. Yes, and that's one naive
So you mean
explanation.
some partial summation is very efficiently taken in this representation.
Yes, yes.
Uh,
And actually, since uh, by increasing d, the free energy or partition function of as a result of the tensor network contraction becomes accurate, right? And that means the fluctuation of Boltzmann weight
yeah.
during the MCMC becomes narrower and narrower, like this. Okay, so
So distribution
here
becomes.
I just plot the energy and magnetization, but if you plot the Boltzmann weight along the MCMC sequence, it, the deviation becomes smaller as well. Okay, and it takes some very fluctuation around some exact value.
Mm. Okay, thank you very much. So is there any other question or comment?
May I ask?
Please.
Okay, so thank you very much for very fascinating talk. So it is question not for the main part, but in the introduction, you talk about the negative sign problem in the quantum circuit.
Yeah.
Maybe
Okay,
next.
here.
So is that the problem for actual quantum computation? So
I mean, it is a very severe problem for simulating the quantum circuit by using classical. Classical.
I agree. But in the actual quantum simulation, it's automatically occurs. So we believe, okay. And
yes, actually, this inference or cancellation is the key point for the quantum computation. Yeah, it is very important.
Okay, thank you very much.
Thank you.
Is there any other question? So may I ask another question? Okay. Is it easy to extend this approach to fermion problem without any essential modification of the formulation?
Yeah, I think so. So, for example,
probably Grassmann representation will be required.
Yes. Okay, here.
Yeah.
Okay, so by using a Grassmann tensor network, we can perform the same simulation without extra cost, I think.
Yeah, that's fine. Yeah, good.
Maybe Akiyama-san can make a
yeah.
comment.
Akiyama-san already tried.
Yes. I agree with the Todo-san's opinion. So that even though we use the Grassmann tensor network technique, the essence of the Grassmann tensor network technique is almost similar to the usual trilogy technique, right?
Yeah.
So that we can rely the Grassmann tensor network technique by using the projector formulation. So I hope we can do the same thing for the Grassmann tensor network case.
Yeah, that's good. Yeah. Now we are doing Grassmann tensor network simulation with Atis-san. He's now here in Niigata. We are very interested in the sign problem in yeah.
Yes.
Mhm.
Okay, is there any other question? Okay, if not, let's thank the speaker again. Yeah, thank you very much. Great talk.
Thank you very much.